Okay, so thank you all for coming. Today we're very happy to have Vladimir Narovlansky, who's going to tell us about semi-classical geometry in double-scaled SYK. Take it away.
Okay, thanks. Yeah, thanks for the invitation. And so I'll talk about this paper with Akash Goel and Herman Verlinde, which is about the semi-classical expansion in double-scaled SYK. And of course, please interrupt me if you have any question or anything. So yeah, let me start just with a reminder and just the definition of the model. So in general, the SYK model is just a model in quantum mechanics with the n Majorana fermions. So they satisfy these anti-commutation relations of the fermions, and they interact all to all in groups of p fermions. So basically, the Hamiltonian, we just go over all the choices of p out of the n fermions, and we write the interaction of these p fermions. By the way, can you see the pointer?
Yep.
Yeah. Okay. Thanks. Okay, and the coefficients are these j's, which are random couplings that I'll specify in a second. So p, so yeah, sometimes it's denoted by q, but it's more convenient for me to use p. You'll see why in a moment. So it can be any number, 4 or anything else in general. But in double-scaled SYK, we take, so we always take n to infinity, but here we also take p to infinity, and we keep this ratio p squared over n to be fixed in the large n limit. So this ratio I'll denote by lambda, and this is so we'll discuss a lot this couple constant lambda in this talk. So I just want to keep in mind that this p squared over n and this is this lambda. So j's, for simplicity, let's take them to be, as I said, they're random. So let's take them to be Gaussian with 0 average value, and with the variance that is normalized in this way. So this angular bracket sub j just means average over these couplings j, this order average. Now in this in double-scaled SYK, we usually normalize it without this factor of 1 over lambda. It's not very important, but just a comment that I added this coefficient of 1 over lambda because in the limit of lambda goes to 0 that I'll discuss in a moment, this bold-faced j will be the same as the coupling used in Maldacena Stanford. So this is just some convenient normalization. Now, naively, so many times this p is not scaled with n when in the large n limit. And another limit that is studied is this large p limit of SYK, where we take first n to infinity and then take the large p limit. So p is large, but much smaller than n. So naively, we would expect this limit to be related to the double scale limit. So in the double scaling, if we take p to be much smaller than n, then this lambda just goes to 0. So naively, we can expect this large p studies of SYK to be related to double scaled SYK when lambda goes to 0. Okay, ds SYK is double scaled SYK. So to make contact with that, first, let me mention that in these studies of SYK, when we don't scale p with n and we consider low energies, then this theory is basically described by the Schwarzschild theory. So it's a theory of where the dynamical variable is in diff S1. So it satisfies, it's a function tau of u that satisfies this condition. And the action is just this Schwarzschild derivative of tau with respect to u. Or another way to think about it is just this JT gravity in the leading order in the genus expansion, so just a disk. And we have some boundary particle that moves in this disk. And its coordinate is described by tau, let's say in this metric, tau of u, where we use the proper time. And then it gives the same action, basically. Okay, so the point is that in this Schwarzschild theory, the correlation functions were calculated in this paper of Mertens, Turiachi, and Verlinde. And so one can expect that if we take double-scaled SYK at lambda goes to 0 and low energy, because here we concentrate at low energies, we may be able to find the Schwarzschild theory. And indeed, so first of all, in double-scaled SYK, it's essentially solvable. So the correlation functions were calculated exactly. And indeed, it was checked that when lambda goes to 0 and we consider low energies, we reproduce precisely these correlation functions that were calculated here. Okay. So one way to think about double-scaled SYK is like a one-parameter deformation of the Schwarzschian or of JT gravity. So there is this parameter lambda, and when lambda goes to 0, it's similar to JT. But so first of all, just a comment that in the Schwarzschian results, the correlation functions are described by essentially representation theory of SL2. So in double-scaled SYK, these correlation functions that I mentioned, they are actually represented by representation theory of a quantum group, UQ_SU11. So this Q is e to the minus lambda. Okay, that's the thing that is better to denote by Q because of this quantum group. But what I want to emphasize is that in double-scaled SYK, these are the correlation functions that are described by this quantum group. They are valid at all energies, all finite energies, and not only at low energies as in the Schwarzschian. Okay, so that's just an important difference. But otherwise, this is like a one-parameter deformation. But the question is anyway, so we see that lambda goes to 0 in low energies is the Schwarzschian, but the question is, one question is whether when we take lambda to 0, but still keep finite energies, whether indeed it is related to this large P limit. Okay. Is there any question in the meantime about the definition and the? Okay, so in this talk, we'll indeed consider this lambda goes to 0 limit of double-scaled SYK, this expansion around small lambda. We will see that it is governed actually, that this is actually a semi-classical expansion. So any correlation function, instead of the time variable, we can represent it in the energy space. So as an integral over intermediate energies. So we will see that the correlation functions in double-scaled SYK, the integrand is essentially some coefficient, here we can think about it as some action that depends on these energies. This is just a function, but importantly, the coefficient is 1 over lambda. Okay, so lambda goes to 0 is governed by a semi-classical approximation. And then we'll see that the leading order, the classical result, is indeed the large P SYK. Okay, so we can think about this parameter lambda. You can have any lambda for double-scaled SYK. When lambda goes to 0, you get large P SYK, and then you can consider also higher orders and see what happens. And I will also discuss some useful geometric description of the various observables in double-scaled SYK, because it will be useful to phrase the various results that I will mention in this geometric way. Okay, in particular. So the plan will be indeed first to introduce this geometrical description, and then discuss this lambda goes to 0 limit first at the classical level, and then subleading corrections to that. And if time permits, we'll also discuss entanglement entropy. We'll see how it goes with time. Okay, so let's first start with this geometrical description. And so there is some lore in SYK that the G sigma action can be thought of as a sort of gravitational description of the theory. So to make it at least somewhat more concrete, let me start with this, with the G sigma of first of SYK and then of double-scaled SYK. So this is a reminder. I'll just emphasize the main steps because they're relatively simple. So when we consider the partition function of SYK, we just have a path integral over these fermions. Tau here is the Euclidean time. So this is the action, and since we this is the Hamiltonian, and since we consider the action, we also add this kinetic term. Now, when we do the average over these couplings J, we assume that they are Gaussian, so we can just complete this to a square. So instead of P copies of fermions, we get P copies of the bilinears in the fermions, okay, just the square of this. And then the trick is to do a Hubbard-Satonovich transformation, which is to introduce two fields, sigma and G, which are functions of the two time variables, tau1 and tau2, both of them. And then we insert this identity, the integral over sigma just forces G to be this bilinear in the fermions. Okay, so we can just replace here the bilinear in psi by G. Okay, so now we just have G to the power P, the usual kinetic term, and this identity that forces G to be the bilinear in the fermion. And then the last step is just to integrate out the fermions since they're quadratic here. So we just get this log of the determinant term. This is from the kinetic term, and this is just the coupling of the fermions to sigma. Okay, and this is just the terms that we had before, the coupling of sigma to G and G to the power P. Okay, this is just the G sigma action of SYK. Now, in double-scaled SYK, we need to do a small change of variables. So from sigma, capital sigma to small sigma, and for G to small g. So essentially, you see that at leading order, this G is just the two-point function of just the theory without any interactions, just of a fermion. But then we need to add this correction. And the idea is to do an expansion when P is large. Okay, so in any case that P is large, we can substitute this change of variables and do the expansion in P. And the point is that previously we had this capital G to the power P. So if we raise this expression to the power P, we just get exponent of small g. Okay, and this is the usual, as before, the sigma G coupling, and this is just the expansion of this log of the determinant term in sigma when we assume that P is large. Okay, so this is all valid up to small corrections when P is large. Okay, and then now again we can integrate out sigma because it's quadratic here, and just get essentially quadratic term in G, and this is a kinetic term. Okay, so when we integrate out sigma, we remain just with this small g. So this is a kinetic term, and this is a Liouville potential, exponent of G. So we just get the bottom line of this is just that for double-scaled SYK, we just get that the G sigma action, so here remain just with G, is a Liouville theory. Okay, is there any question about this?
Do you hear me?
Yes, we have a question.
Yeah. How is that going to be different if you take the conventional large P limit, keeping n fixed?
Okay, good. So this is still true in the large P limit. Yeah, it's a good question. The only difference is that this coefficient here, it just becomes, so in the double scale limit, this is finite. And in the large P limit, this is just becomes something very large. So this is basically becomes classical. That's indeed the point.
I see. So lambda goes to zero limit is
yeah, exactly.
So whether you include fluctuation of this action or not is the basis.
Precisely.
Oh, got it.
Okay, great. Okay, so and one small other change of variables is that we expect this G, which is a function of two time variables. When we take the expectation value, it will depend, of course, because of time translation invariance, it will depend only on the difference. So we are going to define tau to be the time difference and nu the sum of the times. Okay, just a very simple change. But here the kinetic term just becomes this. Instead of d tau 1, d tau 2, it becomes this as usual. Okay, now the geometrical interpretation, that I would like to describe is essentially two-dimensional space. Okay, so instead of in SYK, it's a one-dimensional theory. And so for every 2 points in SYK, we can associate 1 point in 2 dimensions. Okay, so this space is two-dimensional. And moreover, we know that when we quantize gravity in 2 dimensions, we get the Liouville theory that describes the quantum mechanics of the Weil factor. So this is a motivation to consider on this space, this two-dimensional space, we can consider also a metric, which is essentially the flat space metric times this Weil factor, exponent of this small g. And just as a reminder, this small g is related to the bilinear in the fermion. Okay, so we just introduced this two-dimensional metric on this 2D space, and this is the action that governs it. Okay. So now, indeed, okay, that was exactly the question. So indeed, the first comment is that we can write this here p squared over n is lambda, so it's 1 over lambda. So yeah, so for finite lambda, this is finite, but lambda goes to 0 is indeed the semi-classical limit of this Liouville description. So we expect this to the gravity theory essentially to have when lambda goes to 0, it just has some classical geometry basically. Also, as I mentioned, G in expectation values, it's only a function of time, of the time of tau, of the time difference. So we have a symmetry of translations in this nu, the time sum. So if we think about tau as the horizontal directions, the space direction. So sorry, of course the notation is maybe a bit confusing, but tau here is the space dimension, at least in this signature, and nu is the time direction. Then we anyway will have translations. The time translation on the boundary will translate into time translations in this 2D geometry. Okay, and here I draw it as a strip because indeed we'll see that lambda goes to 0 in this construction gives us indeed just ADS, two-dimensional ADS. And for larger lambda, we of course have fluctuations, so the geometry fluctuates. We can still consider what is the average metric, and that's what we'll do most of the time. But of course now it becomes fluctuating. Yeah.
So the space of parapoints is what's called kinematic space, right?
Yeah, exactly. Yeah, I'll comment on that indeed. Yeah.
Oh, okay. So I shouldn't think about this as the physical ideas, but something related to it by some random transform or something like that.
Right, exactly, yes. So I'll have actually a slide there commenting on the precise relation to kinematic space, but yeah, it's a good question. So the space is kinematic. Okay, so yeah, maybe I'll say a few more words there. Yeah, I still honestly should say that there could be still some relation to the more usual, like also to the bulk, even maybe more directly, because basically like in the one way to derive the Schwarzschild is to start from the G sigma. So so maybe there is a way to to take some small time limit and derive from this also a relation to the Schwarzschild and so on. But okay, this is just a comment. I don't know how to make it precise at the moment. We can think about it more as a kinematic space indeed. Yeah, and any correlation function in double scale SYK we can also describe as a correlation function here, basically. Any other questions? Okay, so let's start indeed with the lambda goes to 0 limit. So let's start to look at it from the double scale SYK point of view, okay, and see that it's indeed related to the large P limit. So as I mentioned, in double scale SYK we know the partition function and the correlation functions. Let's start with the partition function, by which I mean just the thermal partition function, trace e to the minus beta h, averaged over J. Now the energies in double scale SYK, it's convenient to parameterize them by an angle theta. So theta goes from 0 to pi. This is just a parameterization of the energies. They're essentially proportional to cosine theta. And again, Q here is e to the minus lambda. Now in the lambda goes to 0 limit, this is just becomes lambda, okay? So it's basically just cosine theta over lambda, and the scale is set by this J. Now the partition function is just the sum, of course, over the energies, or equivalently integral over these thetas, and just change of parameterization, e to the minus beta times the energies, which are these guys. And then here we have some measure as a function of theta. So this measure is essentially the density of states that was calculated in double scale SYK, but here it's written in terms of theta. Just to say what is the details of the measure are not super important for us. Just to define it, these objects here are called the Q Pochhammer symbols. They are just some Q deformation of the usual Pochhammer symbols. They are defined by this infinite product. And here, this is some dense notation that means that there are 3 Pochhammer symbols here, where A equals to Q, e to the plus 2i theta, and e to the minus 2i theta. Okay, so it's just a product of 3 Q Pochhammer symbols. Okay. Now, to do the small lambda expansion, the key is to know that these Q Pochhammer symbols have an asymptotic expansion for small lambda, where the leading behavior is just this e to the -1 over lambda times a dilogarithm. Okay, so for every such Q Pochhammer symbol, we can just replace it by a dilogarithm at leading order. So the partition function is just this integral over theta, exponent of -1 over lambda times the two dilogarithms from the e to the plus and minus 2i theta, and this is just the energies. So recall that the energies also had 1 over lambda. Okay, but so indeed we see explicitly that in double scale SYK, we see also in the correlation functions here, it's the partition function that lambda goes to 0, it appears as an overall coefficient, so it's a semi-classical limit to take lambda goes to 0. So it's just a saddle point basically. Okay, so we can now just write the saddle point equation, just take a derivative of this with respect to theta. It's actually something very simple. And the only thing that I will also do is to shift theta. So I'll define this v. It's just theta shifted. Okay, it's just a redefinition. This v is essentially theta. And in terms of this v, the saddle point equation becomes this equation. Okay. Now you may be familiar with this equation from the large P analysis in Mendelssohn and Stanford. There, it's essentially a definition. It's just a definition of v. Okay, so v is just another parameterization of the temperature. Okay, so when beta j goes from 0 to infinity, v takes the range from 0 to 1. Okay, so since beta is 1 over the temperature, the low temperature limit corresponds to v goes to 1. Okay? The high temperatures, v goes to 0. But here it's not a definition, it's actually just the saddle point equation. So it's really an equation relating the temperature to the dominant energy, right? So in the saddle point, we have some dominant energy, and this is exactly V. So V was related to theta, which parameterized the energy. Okay, so that's the interpretation of this equation in our case. It's just the saddle point equation. Okay, so now all that is left is just to plug back the saddle point equation in this exponent that we had before. The sum of the dilogarithms is actually just a polynomial. So this is this polynomial, and then the energies which were cosine theta just becomes this as a function of V. Okay, so basically this result, this saddle point, is exactly the what Mendelssohn and Stanford obtained in the large P result. So indeed, we just reproduce large P at the leading order. Okay, it's just to emphasize, this is just a simple saddle point analysis of, like, we don't do even fields, right? It's not saddle point of functions. It's just some integral of numbers, and we just get the saddle point value and plug it back. That's it. Any question about this saddle point?
Maybe a vague question. If you want to fix B and be microcanonical, can you also say that you have classical limit? Is there a saddle point there, or?
Okay, good question. In the microcanonical ensemble,
that's sometimes tricky in gravity, because the canonical ensemble is classical, but the microcanonical is not always.
I see.
So I'm wondering if you can see that here.
Yeah, it's a good question. I'm not sure, actually. Yeah, would be interested to look at it. Yeah, I'm not sure.
Okay.
It's also governed. Yeah. Okay. Yeah, it's a good question. I don't know. Okay. Any other questions about this? Is it clear? Okay, so now I will move on to the two-point function. So the two-point function is similar, but I first need to say a two-point function of which operator. So basically, we just want to take strings of fermions, right? These are the natural operators. So we just take strings of p tilde fermions. Okay, so p tilde is essentially the size. This is the definition. It's just the size of the operator, basically. But the only modification is that it's convenient in double scale SYK to look at operators that take a similar form to the Hamiltonian. So we just also add these Gaussian coefficients. But okay, this is more of a technicality. The more important point is that these are just strings of p tilde fermions, and that's it. And for them, we also define this analog of lambda, which will be lambda tilde. It's just like proportional to p tilde. Okay, it's not There's nothing new here. It's just a definition. And also Q tilde, which is e to the minus lambda tilde. Okay, these are some parameterizations, but they're not, it's just similar to the P and lambda and Q that we had before. So yeah, so lambda tilde is just the size of the operator, basically. And then we'll look at the two-point function. Here I consider the unnormalized two-point function. So that's why it's denoted by G tilde. And at the end, of course, we need to divide this by the partition function. So this is the two-point function of an operator times 0 and an operator time tau. Okay. Okay, now for this two-point function, it was also, again, it's known what it is in double-scaled SYK. So if we think about the Euclidean time as a circle, then we have two insertions of operators, and we consider the energies that flow here and here, okay, theta 1 and theta 2. So again, it's just in the energy representation, it's just the integral over these two energies, the coupled to the time differences, which are tau and beta minus tau, if we're in the thermal ensemble indeed. And the only thing that remains is basically the matrix elements of the operators, and they are just, again, some combination of these Pukamer symbols. And again, the point is that when we take lambda to 0, we expand this using the Dye logarithms. So we just have some integral over the energies, and then we have 1 over lambda that multiplies something. This something is, again, some combination of the Dye logarithms and the two energies. Okay, it's really the same as before. Then we can write the saddle point equations for theta 1 and theta 2 and get these two equations. Now, okay, at least as far as I know, I don't know how to solve this equation exactly, but the point is that these equations are valid for generic operators, okay, for any operator size. Now, if we don't want to back react too strongly on the geometry, if we want to concentrate mostly on the geometry, we can consider light operators or probe operators. And then we need to take small lambda tilde, okay? So the point is that now we are going to restrict to small lambda tilde, and here this is going to simplify. So yeah, again, lambda tilde is the size of the operator. Now there is only one subtle point here in this analysis, and the point is that if we want to do this saddle point analysis as a small expansion in lambda tilde, we cannot just take two different saddle points, but in fact at leading order we need to take the same saddle point value, okay, the same theta, and then at subleading order in lambda tilde there will be a different value of these two parameters, theta 1 and theta 2. Okay, so alpha is like the difference between theta 1 and theta 2. Actually, it makes sense physically, right? Because like if we take a light operator, it will not change the energy too much. So that's why at leading order this is the same. But the subtlety is that even though they differ only at order lambda tilde, the two saddle point values, this alpha will enter in the saddle point equations already at order lambda tilde to the 0. Okay, so it will essentially come to a lower order. It will enter a lower order when we plug it back. Okay, so then the saddle point equations just simplify, okay? And the sum of these saddle point equations just gives us the same equation. So V is related to theta just as before, and we get the same equation that relates the temperature to the average energy. And the difference of the equations will just fix for us this alpha. Okay, and the rest is the same. We just plug in the saddle point back, calculate F up to order lambda tilde. Okay, so we'll get here essentially something that goes like lambda tilde over lambda. And this is this power that we get here. Okay, so once we normalize by the partition function, we just get this two-point function after plugging back the saddle point. That's it. Now, if we phrase it in terms of this e to the g, so this small g, just a reminder, it's in the Liouville action, that was the bilinear in the fermions. We just need to strip off this power of the operator size, and we just get this two-point function, which is exactly what, again, Madsen and Stafford got at large P. Okay. Okay, any question about this? Okay, so the only thing that I want to do now is to, in the first part of the talk, is just to phrase this in this geometric language that I mentioned before. Okay, so now we just look at this two-dimensional space. So I just now going to rescale tau, which was the horizontal direction, to define the sigma, just rescale by beta, and need to define this new tilde. The reason that I'm doing that is just because if we are at low temperature, let's start with low temperature, then this beta becomes very large. So if I want to probe also like different distances, I need to scale it in this way. So then when V goes to 1, which is the low temperature limit, the metric, which is e to the g, just becomes this. Okay, just essentially this. Here the V goes to 1, so the pi over 2 minus something, the cosine becomes just a sine. So we just get essentially 1 over sine squared of sigma. Okay, this is exactly, if you draw this strip, sigma goes from 0 to pi. This is exactly the metric of two-dimensional ADS. Okay, as I promised at the beginning. And of course, another way to see that is just to consider the Ricci scalar, which is essentially this Laplacian of G. Okay, this is the usual relation between the Ricci scalar and the Weil factor. So at lambda goes to 0, it's just a negative constant. It's just a constant minus 2j squared. So indeed, it says that it's just ADS2. So two small comments. One is that 1 over j is the coupling in SYK, sets the radius of ADS. And the other comment is that if you recall, we mentioned that in any case, translations in nu become isometries of the space. But in this case, actually, we get more isometries. We get all the SL2 isometries of ADS. Okay, so but this, of course, this is not guaranteed. This is just happens in the lambda goes to 0 limit. In general, we expect only these translations, not the full SL2.
That's for any V?
So that's for, okay, good. That's for V goes to 1. Now let's discuss any V. Okay, good. So what about any V? So for any V, this cosine doesn't simplify to sine, but still, so this was the e to the g that we wrote. So if we calculate the same Ricci scalar, we get that it's still minus 2j squared. So that tells us that it's still at least a patch of ADS. Okay, so any V is going to be a patch of ADS, but not necessarily the full ADS. So to see what patch it is, we just need to see where this metric is going to blow up. So this metric blows up in two values of tau. So again, recall that tau is this horizontal direction. And for general V, the distance between these two values of tau is beta over V. Okay, so in general, this is V is between 0 and 1. So in general, this is more than beta. This is greater than the beta. While for V equals to 1, it was just beta. So if we decide that we anyway always restrict tau to go from 0 to beta, then we now see that the place where the metric blows up is a larger range than what we had before. So that means that what we see is just a smaller patch of ADS where essentially the boundary is just pushed into the bulk. Okay. And this actually can remind you what happens in JT gravity, because there also when we increase the temperature or decrease beta, the boundary gets closer into the bulk. So it's actually similar to what happens here. Yeah, I think I actually wrote the formula before for JT, so you can see it explicitly. It's not very important, but yeah, you can see it explicitly that the size of the boundary in JT is just proportional to beta. So it becomes smaller when beta becomes smaller. Okay, this is just a comment. Yeah, so okay, so that's the case for any V. It's a patch of ADS, but only at leading order in lambda, when lambda goes to 0. Okay, now indeed, let me just make a connection to the kinematic space discussion. So indeed, in kinematic space, what people study is the space of, at least in 2 dimensions, it's just the space of oriented geodesics. So, or equivalently, if we're in 2-dimensional hyperbolic space, the geodesics are fixed by the 2 boundary points. So kinematic space in 2-dimensional hyperbolic disk is exactly the space of 2 boundary points. And this is exactly the space that we considered indeed. Now, one difference is that in kinematic space, people usually study the length of this geodesic S, or equivalent in the boundary, it's the entanglement entropy. And then usually the metric that is defined in kinematic space is the second derivative of this length with respect to these two endpoints U and V. So, so naively, this is the metric that is used usually in kinematic space, while we defined it in terms of the 2-point function. However, at least at leading order, it actually agrees. So at small lambda and low temperature, we get actually the same answer. So the metric in kinematic space is 1/sin² of the difference between V and U over 2. And we also get this 1/sin² of sigma a moment ago. So yeah, and sigma is what corresponds to this variable because it goes from 0 to pi. Okay. Yeah, any other question? Any questions about this? This was the leading order in the lambda. Okay.
So you get the SL2 symmetries for any value of V, right?
Yes, right. That's right. Yes, yeah. Actually, it's right. Yeah, yeah. It's a good point. So that's related actually to this. There is some unpublished work of Stanford, right, and Henry Lee and I think and Yang, and they basically define this fake disk, fake hyperbolic disk.
Oh, yeah.
Right. So that's yeah. So I guess that's another way to see that, right? Exactly. That you still get some SL2 basically. Yeah.
Is the fact that you still get an SL2, does that mean that the theory is different than JT gravity at finite cutoff?
Okay, good. Yeah, that's a good question. I think it is still different. Yes, because they're also right. We see that the density of states and so on, things become more a bit more weird. So yeah, I would say it's still different, right? Yeah, and the question, yeah, which I guess I'll mention in the future directions, is indeed how to precisely modify JT to see this rather than what you get in finite cutoff.
It seems hard to write down anything except the Schwartzian that respects the symmetry breaking.
Right. I guess the only option, yeah, if we want to change only the boundary theory, yeah, I guess we can only look at some other things that will respect the SL2. Yeah, it's not clear what we can write. Yeah, indeed. Right. Yeah. So yeah, that's an interesting question. Yeah, any other questions? Okay, so if not, so let's move to the next order correction. And so until now it was mostly indeed like at least the correlation function, it's a known result. It's just to see that it agrees with large P. But now we'll calculate corrections and we phrase it in this geometric language, which was rather useful. But now let's see what happens at the next order. So usually, if we want to go to the next order in saddle point, we just calculate the one loop determinant. However, what I would like to mention is that here, essentially, the corrections come from, there are more sources of correction. So in addition to the one loop determinant, the analog of the action, which is what we had in the exponent, also gets corrected if we go to the next order in lambda. So sort of the action itself gets a small correction. So we also need to take that into account. And in fact, there is something very subtle that happens, and I will mention it, at least the idea of why it happens, is that the saddle point structure, we also need to take that into account. And in an indirect way, it will affect also the subleading correction in lambda. That of course, doesn't happen when we do a saddle point. It happens here for a very indirect reason. So yeah, it's a bit subtle, but it's actually very important to get the right answer. Okay, so I'll mention this briefly in a moment, but first let's start with the partition function where this doesn't happen. This third effect doesn't happen. So for the partition function, as I said, we just need to calculate the corrections to the action. So there are two sources of corrections. One is this Q-Pocamer in this asymptotic expansion. We have this in addition to the Dal logarithm at order lambda to the 0, we have this additional term. So we need to take that into account. And also the energies themselves, they also depend on this Q, which is e to the minus lambda. So we also need to expand this in lambda and get another small correction. Okay, so basically, but this is not a big difference. So the partition function is still this integral. These are the three terms that we had before, the 1 over lambda, and now we had this correction from the energy and this log. Okay, but this is still the same. We just use the same saddle point here and just plug it back and calculate the one loop determinant. Okay. So we just use the one loop determinant and the saddle point and plug it back to the action. Sorry, to the partition function, and we get this value. Okay, so this is a straightforward calculation, and for the we can phrase it also in terms of the free energy. So these two terms are what we had before, the large P limit, and now we have these three additional terms, and these are actually can be thought of as like small corrections to the large P result. Okay, so this is the next order correction to the partition function, basically. Okay, any question, or that I guess is okay. Now let me just mention this subtle point that happens for the 2-point function. So the beginning of I'll just mention the idea. Of course, I'll not do any calculation, but I think the idea is a bit subtle, so I'll just mention it. So we have the same energy integral representation of the 2-point function, where before we had this e to the minus f over lambda. Now the correction to the action, which is order lambda to the 0, is denoted by this small h as a function of theta 1 and theta 2. So this is the correction to the action that we needed to take into account. That's fine. But the subtlety is that when we do the expansion in this small lambda tilde, so now we talk about lambda tilde, it will eventually affect lambda, but we'll see in a moment how. So when we discuss this small lambda tilde, which are light operators, recall that I mentioned that the saddle point values, higher orders in lambda tilde actually enter in the saddle point equations at lower orders when we plug them back. There is this strange effect that happens. So now if we're interested up to order lambda tilde, we need to work up to order lambda tilde squared in these saddle point values. So in addition to these thetas and alphas, we also need to determine this eta and gamma. Okay, so these are just two other parameters that we need to fix by the saddle point equations. Okay, that's fine, but the point is that they will not affect the order lambda tilde term in F, which gave us this lambda tilde over lambda term, but they will affect the order lambda tilde in H and in the one loop determinant. Okay, why is it important? Because if you remember, if you write this capital G as something to the power lambda tilde over lambda, we write it in this form because to get e to the small g, we need to strip off this lambda tilde over lambda power. This is the size of the operator. Then something that is a small correction in lambda to this leading order large P result will actually, when we take this power lambda tilde over lambda, it will become a small lambda tilde correction. Okay, so that's why this small lambda tilde correction gets translated to this small lambda correction. Okay, yeah, if you have any questions, please ask, but I hope it was clear, but that's just to emphasize why there is a small subtlety here and how we get small lambda corrections to this result. So we calculated this G1. I will write it in a different form, actually, in the geometric representation. So in this geometric language, recall that we considered the Ricci scalar, which is the curvature, and at leading order, it was just a constant, right? This was just ADS. Now we see that there is a small lambda correction to this result, and we'll denote the coefficient by delta R. So this is a small correction to the Ricci scalar in this two-dimensional geometry. Okay, now this so this calculation of G1 gives us this delta R. Okay, and it gives some expression. Okay, of course, It's not super short, but it's just some analytic expression as a function of tau, basically. Okay, so the point is just at one loop, we get this small correction analytically. And now we can study this also in various limits. So first of all, let's consider what happens at low temperature. Okay, so at low temperature, this correction to the curvature gets simplified. So let's examine what happens. So, sorry. So what happens? So recall again that we have this strip, and tau is the horizontal direction. Here I plot this correction to the Ricci scalar as a function of this horizontal direction tau. Okay. Now, sorry, any question?
No.
Okay. Now, when tau is small, this is still, the correction goes to 0. Okay, this delta R goes to 0. So this is still essentially asymptotically ADS. Now, when tau becomes larger, there is some functional form, but eventually it becomes something linear. So this function is just something linear for large tau. But what it tells us is that when we go for larger and larger tau, deeper into the bulk, this correction becomes very large. And so this semi-classical expansion in lambda breaks down. So this approximation is already breaking down, and we can think about it as the theory becoming strongly coupled here, deep in the bulk. Okay, so we cannot trust this at low temperature, deep in the bulk. Okay, now, however, this geometry is still expected to respect a Z2 symmetry of reflection in this horizontal direction. So that basically corresponds to tau goes to beta minus tau. Okay, so here I just show this correction delta R as a function of tau over the full range, and not in this expansion at low temperature, but just at some fixed value of the temperature, which gives V equals to 0.99. Okay, I just plug in V equals 0.99 in this formula and just plot it. So you see that indeed it's reflection symmetric. So it's like a two-sided thing. And here it still looks like it's linear, but this linear dependence is going to break down at some point because of this symmetry. Okay, now this is a bit of a sharp behavior because of this linearity that breaks down. But of course, if we go to higher temperature, it will be something more smooth. So for example, for V equals to 0.6, this is some more smooth function as a function of tau. Okay, but in principle, what it tells us is that this curvature, when we go into the bulk, it becomes more negative. It's not the constant curvature that we saw before, but at subleading order in lambda, it already becomes something non-trivial, and indeed this SL2 is broken. So we only have translations in the time direction symmetry. Okay, any question about this? Okay, if not, let me now discuss what can we say about finite lambda. Okay, so until now we discussed the leading order, which is just the large P result, and then we also found analytically the subleading order, the one loop result. Can we say anything about finite lambda? Okay, so of course analytically it's going to be hard, but let's see what we can still say. So naively, this e to the g that appeared in the G sigma action, recall it's the 2-point function of a single fermion. So this was the relation that related lambda tilde to p tilde. So if we take p tilde to be 1, which is a single fermion, then when we divide it by p, it will just go to 0 because p is large, also in the double scale limit. So the point is that for finite lambda, this lambda tilde will just go to 0 when we want to relate this 2-point function to the variable that appears in the G sigma action. So at least formally, we can define e to the g, the expectation value, to be the 2-point function when we strip off this size of the operator power that we always had and take lambda tilde to 0 or q tilde to 1. Q tilde is e to the minus lambda tilde. Okay, so this is some definition, at least, of this two-dimensional metric as a function of this two-point function. Okay, now what can we say about it? So first of all, there is actually a simple physical meaning to this geometry in that case. So the curvature, which is the Ricci scalar, the bottom line is that it's actually related to fluctuations in the energy of light operators. Okay, so the curvature in this two-dimensional space is just fluctuations in energies of probe operators. Okay, now to explain why this is the case and to define it more precisely, let's first of all consider the following. So recall that we looked at the unnormalized two-point function before dividing by the partition function G tilde, and it had some energy representation, right? It had some two integrals over the energies and some integrand. Doesn't matter. We had some expression. So let me define expectation values with respect to this two-point function. And by this, I'll just mean that for any insertion x will just do the same two-time integrals with the same integrand that we had in the two-point function, but we will also insert x in the integrand. Okay, this just defines expectation value of x in the two-point function. Now, what I mean by this statement precisely is this formula. So, except for these prefactors that are not important, the Ricci scalar is just basically okay. So we take q tilde to 1. That's the limit that we always need to take. But it's the expectation value in the two-point function of the energy difference squared minus the expectation value of the energy difference, all of this squared. Okay, this is exactly the fluctuations in the energy difference. So E1 and E2, if you recall, these are the two intermediate channel energies. So E1 minus E2 is just the energy of the operator that we inserted in between. So this is the energy of the operator, fluctuations of it, the variance of it, in the limit where q tilde goes to 1, which is the limit of light operators. Okay, and one more comment, which is why, okay, I didn't prove it, but I can explain quite easily why it makes sense. So the derivation is quite simple, but the basic idea is just that this Ricci scalar is the Laplacian of this e to the g, right? So this was the relation of the curvature to the Weil factor. So the Laplacian means that we just need to take two-time derivatives, and every time derivative just gives us a factor of an energy. So that's why we get energy squared. Is this interpretation clear, or are there any questions about it? Okay, so now I can, of course, this is something that, okay, at least I don't know how to calculate it analytically, but I can evaluate it numerically. So let's show it numerically. So the plots that I'm going to show here are the full Ricci scalar as a function of the horizontal direction. Okay, so recall that the leading order, the classical result, these are the black circles. This was just flat ADS, not flat, but I mean rigid ADS. So this is just a constant negative curvature. This is the leading order. Then we calculate the one loop result, which was the subleading order in lambda. And this is this red plot, okay? So the red curve is just this formula that I had before. This one, just plotting it. So this we know analytically. And now we evaluate the expression here numerically, okay? So we need to take q tilde to 1. Of course, I cannot do that numerically, so we're going to plot it for various values of q tilde that are just getting closer and closer to 1. So here you see just several values of q tilde. These are these colored plots, but they, of course, just you see that they converge quite nicely to some value. Okay, so we are going to compare three things. The leading order is obvious, but we're going to compare the one loop, the red thing, to the limit of the numerical evaluations. So the plot here, so both plots correspond to V equals 0.6, so it's just some finite temperature. And the two plots are for different values of Q or lambda. Again, they're related. Q is e to the minus lambda. The first plot is for q equals 0.36, which is lambda close to 1. Of course, lambda close to 1 is not very small, but you see already here that still the one loop, which is the expansion in small lambda, is still not that far from the actual numerical result. Okay. Now, if we're going to take q to be closer to 1 or lambda closer to 0, so we take q to be 0.8 or lambda to be 0.2, then this is smaller. It's not super small, but it's smaller. And here we already see that the red plot becomes very, very close already to, let's say, the green one. Anyway, to the bottom one. Okay. Okay, good. So this is like another test of this analytic formula that I wrote before. So it shows that the one loop result is indeed when q becomes closer to 1, it's actually a very good approximation of it. Okay. Question? I think. Okay. Yeah, sorry, I thought I heard something. Okay. And the other point that you can ask is what happens. So this is, of course, if we take lambda smaller, we'll get a better and better approximation. But what happens when we change the temperature? So now we fix lambda, but we change the temperature. So to check that, here I plot the same things, but for v equals 0.9. So that's already closer to 1, which means that the temperature is smaller. Okay, so now we consider a lower temperature. Okay, so here you see that these are the same values of q's as before. And you see that, for example, if we compare this plot to this, you see that the approximation is much worse. This is the one loop, and it's much farther than the actual numerical evaluation. Here it's also a worse approximation, but not that bad. But the point is that as we lower the temperature, the approximation, the one loop approximation becomes worse and worse. And actually it's not surprising, right? Because when we discuss it analytically here, we saw that it increases when we go into the bulk. And we said that it becomes very large, so we cannot trust the small lambda expansion. So indeed, here you see that close to the boundary, it's still, the results are close, but when we get into the bulk, they already become worse. Okay, they're very bad actually here. Okay, is there any question about this? Okay, okay, I'm not sure. So do I have time? I'm not sure. Actually, it looks like it's 3, which is 12.
Yeah, we started a few minutes late. Take your time.
Okay, so maybe I'll just, I will not go into all the details. I'll just mention the last point. Okay, I'll just mention the entanglement entropy calculation, but maybe without all the details. Okay, I'll just say what is the idea of the last point. So I'll just take like 3 minutes for that, or 5, something like that. Okay. Okay, so here, if we want to calculate entanglement entropy, okay, so now I'm not considering the 2-point function. I'm just now going to discuss the entanglement entropy. So now we consider SYK, so it's a quantum mechanics. So we want to divide it into 2 subsystems. And the natural way to do that is just to take 2 copies of the system. So we take 2 SYKs, and of course, the most familiar state for the 2 copies of the system is the thermofield double. We sum over the energy eigenstates and put the same state both in the left and the right system. And we weight it by this. A simple way to describe it is as familiar to do just a Euclidean integral over an interval of size beta over 2. And then we have the 2 systems on both ends. And this defines for us exactly the thermofield double. Now, a generalization of this state is it's called sometimes partially entangled states or PETs. They are described by a similar construction, but now with the insertions of operators. So we are doing essentially, again, I will describe, this is a formula, but I can just describe it in this Euclidean version. We're just doing a Euclidean evolution of time beta left over 2, insert some operator O, and then do another Euclidean evolution. And that defines for us another state on these 2 copies. Okay, and this gives us a partially entangled state. For O equals to 1, it just reduces, of course, to the thermophile double with beta, which is just the sum of beta left over beta right. Okay. Now, if we want to calculate the entanglement entropy of the two copies, we just trace, let's say, the left side. So in picture, it means that we are doing the bra and the cat, and we just glue the left side. So we just remain with the density matrix on the right side. Okay, so this is an operator defined on these 2 points. Okay, this is like the two sides of the two right. Okay, in our case, O is just Hermitian, so it's so you see that O dagger is O, so it's just two insertions of an operator O to define this density matrix. Now, the thing that we calculated is essentially Renyi entropies, but a modular version of the Renyi entropy. This is, for example, in the Renyi discussion of Ryota Kayanagi, this is the more convenient thing to look at. But okay, this is just a different definition of the Renyi entropies, and they are defined just by a derivative with respect to n of Zn. So Zn is trace of rho to the power n. For example, for n equals to 1, we just take a trace of rho, so we connect these 2 points, and we just get a 2-point function of this operator O. And for other n's, Zn will just be a 2n-point function. And now this version is convenient because the entanglement entropy is still the limit of n goes to 1 of these modular Renyi entropies. But the advantage is that it's unaffected by the normalization of rho. So we can also use an unnormalized density matrix if we want. Okay, now we calculated it in the lambda goes to 0. Basically, these modular Renyi entropies for lambda goes to 0. And okay, in view of time, maybe I should not get into details, but basically, the idea is just that these 2n-point correlation functions, at least for light operators, we have large n factorization, so it just becomes the product of n products of 2-point functions. Okay, so it will just we'll just need to pair pairs of operators. So if you plug just n such 2-point functions in this formula here, basically just the idea, we will get this modular Renyi entropy, and it is defined in terms of Vn, which is just V that corresponds not to beta but to n beta. So V was defined by relation to beta, and this depends on this variable tau and beta. So tau and beta are just a redefinition of beta left and beta right that I wrote before. It's convenient because tau is the distance between the two operators, like in the 2-point function. Okay, and one test of this formula is that if we take low temperature here, we reproduce the result for this entanglement entropies that was found for the Schwarzschild in this paper. Okay, but in general, it holds not only at low temperatures. Okay, it's at any temperature, but for a small lambda. Okay, yeah, I see that it's more than 3 minutes. Okay, so let me skip the heavy operators and just go to the conclusions. So yeah, so the bottom line is that we saw that the large P limit, it corresponds to the classical limit of double-scaled SYK, where we take lambda to be small. But in general, we have some semi-classical expansion for small lambda. And we calculated analytically the one-loop correction to it. And found numerically it for finite lambda. So it's interesting to understand better what happens at finite lambda, because it was more of a formal definition, but it looked like it works quite nicely, at least in these numerical plots that I showed. And we found it useful to phrase it in terms of this metric in kinematic space that we discussed. And there are quite a few directions that would be interesting to study. So here we studied just the SYK, double-scaled SYK of Majorana fermions, but there are many other versions. For example, we can take a complex fermions, and then we have a U1 symmetry. And there are other versions with global symmetries. There's also supersymmetry. There's an n equals to 1 and n equals to 2 versions of double-scaled SYK. And there is quite a rich structure there. So yeah, and when we have global symmetries, usually we have gauge fields in the bulk. So it will be interesting to see what happens in this description that we had. Also, we discussed just one boundary, right? That was the analog of just taking a disk. But if we have several boundaries, then this is, of course, highly motivated because this is what's related to the spectral form factor. And we can learn about energy fluctuations and so on by considering these observables. So it will be interesting to see what happens to the structure that we studied when we have several boundaries. Yeah, so that's like several copies of SYK. And then indeed we discussed this, the how to understand it, how to modify JT gravity to give these calculations that we mentioned. Okay, yeah, so thank you, and that's it basically.
Okay, thanks for the great talk. Let's thank Vladimir.
Thank you.
Any questions for him?
In the
Sorry,
case
Charles,
of,
go ahead.
in the case of the spectral form factor, so what is there a similar derivation than the one you did to get the Liouville action?
Yes, so right, so yeah, so in that case there is something similar that we can do. We need to introduce G's that relate the, it's like the wormhole, what is called the wormhole in these studies. Yeah, it's like G left right and G left left, G right right. Yeah, so we can do something similar to that indeed. Yeah.
And do you, I mean, is it done or is it can be done?
No, actually, yeah, actually I'm trying to recall if it was done for the Liouville form, and they cannot recall that actually.
Okay.
I think there's some discussion in Maldacen-H, but that's just for large P. It's not the double scale theory.
Right. And do you remember if it also has this like n over p squared in front of everything?
Oh yeah.
That's why I wonder.
Just have to scale the off-diagonal terms appropriately, right? Then it probably does.
Say again?
You probably just need to rescale to just scale the off-diagonal G's appropriately, and then it probably works.
I see. Okay. Yeah. Right.
I guess I was curious. Is there can we already know like the number of fields we're going to have, and what is the theory? Because you know the geometrical interpretation of, I mean, the whole geometrical interpretation came from this Liouville action and the interpretation of G as being the Weil factor. Well, I guess what is going to be the geometrical structure in the case of the spectral form factor? Do you have like multiple? I guess I don't know how it works.
Yeah. So right. So actually, it's not obvious to me that it will be something similar, completely analogous to that. Maybe I'm not sure, but maybe because so actually we also studied like this something like the spectral form factor in double scale SYK. And there, if you take two copies, let's say the connected components are actually suppressed by 1 over n. So not only lambda, but also 1 over n. And if I remember correctly, that also happens in the double scale limit. If I remember correctly, also in the double scale limit. Let's see.
So does it mean that the leading order is factorized?
Yeah, the leading order is for sure factorized indeed, but I'm just trying to recall whether the subleading order is controlled by lambda or by n. And then yeah, no, maybe indeed, yeah, maybe indeed if we rescale correctly, it's true. Yeah, maybe it's true that it's by lambda still.
Just looking at the paper to see that result, and I see your name on that paper, so that's probably not. So, but you know, you have these non-geometric wormholes.
Right,
so
exactly.
Right. So somehow this spectral form factor should not really have a geometric value.
Yeah, exactly. That's the point, right?
Yeah.
Right.
I see.
Yeah.
So yeah, so maybe it's like some on top of this geometry there are some, on top of the factorized geometry there are some fluctuations that relate the two sides, but it's not just pure geometry. Yeah, right.
So I'm wondering if you can scale the time with lambda or with n.
Ah, good. Right.
Did somebody try to do that? Because this is relatively early times for the physics of the spectral form factor, I think.
By the way, maybe I can stop the sharing for a moment so that I can see you better also.
Oh
Yeah.
Okay, then I'll see you better. Okay, good. Yeah, so you say if we take the two, right, so in the spectral form factor,
I mean, if you take the double scaling limit, give you the time fixed. I think the sort of universality of lever repulsion and all of that goes away. So I'm wondering if anybody tried to scale the time as well in the double scaling limit. I don't know a priori that it makes sense, but naturally.
Yeah, no, if we get like finite answers, then I guess it's good. Yeah. We didn't try to actually, yeah, we didn't try to scale the time indeed. So yeah.
I guess you can try that in the real description, maybe, I'm not sure.
Right, maybe that's the easier way to see that it will give something finite. Yeah, actually, like the leading order is relatively simple. It's like we take two such systems and okay. The thing, no, sorry, it's not that easy to see from this description. From this, we usually analyze it with moments, but then it's hard to see it because we need to sum them. And what you're saying to scale time is actually sensitive to the summation. Yeah. So yeah.
I don't have any sort of bright ideas. I'm just speculating here.
No, yeah, but it's a good, if there is some rescaling of time that gives something finite, that would be very nice. Yeah, I think it's I mean, it could happen. Yeah.
But I think the interesting physics is the physics of discrete levels, and if you take them to infinity, then that just goes away.
So say again, I couldn't hear.
So the interesting physics is that of discrete levels. So if you take an infinite system, all of that goes away. So
yeah, I see. Yeah, to see the discreteness, right? Yeah. That's the interesting physics, but the very hard one to see usually analytically.
Can I ask about the entanglement entropy?
Yeah, sure.
So you had two expressions for that in different regimes governed by two different diagrams.
I have another physics I have to run. I'm sorry.
Sure. Okay. Thanks. Yeah.
I talked to Micha this morning and he said hi.
Okay. Thanks. Nice. Okay. Thanks.
Yeah, I was just wondering, is there a meaning or an interpretation to the transition between the two?
Whether it's smooth, right? Let's see.
Like, is there some kind of information paradox that gets resolved by the transition between the two?
I see. Right. Let me try to think about it. I mean, the origin of the transition is just that when these 2 points become closer, then the dominant thing is that we don't pair this one with this, but rather this one with this.
That's right. That's the usual mechanism that resolves the information paradox. So right. when you have some operators that are probing a black hole background, the way, as you know, the way in which the information paradox gets resolved is by this geometric transition that happens. And in the operator, in the boundary side, that corresponds to a different kind of pairing of the CFT operators in the product expansion. Right. So here it looks like there's some kind of paradox that you would run into if you didn't have the right hand diagram.
Yeah, that's like what gives you the minimum between two expressions rather than one that just grows. Yeah.
That's right. That's right.
Yeah, no, I agree with that. Just trying to think how to phrase it precisely as yeah, I see. So you're saying that it's like the one-sided entropy would otherwise like grow too much. Yeah.
Yeah, I would expect that something like that would be true, that when the temperature kind of becomes very large, the entanglement of the quantum fields is larger than it should be. And this right-hand side diagram is kind of modulating that and giving you the microscopic entropy. But I'm not sure if that's the right interpretation. It's kind of an interesting setup, because here in the expression for the entropy, it's very hard to see the dilaton field. And in JT, usually the dilaton is what plays the role of the entropy, or of the black hole entropy.
Yeah. So, right. So, but this is in the bulk, right? The dilaton is in
That's
the
right.
bulk.
That's
yeah,
right.
so there was a discussion. Okay, so in the low temperature limit, what you're saying is actually, yeah, it's made precise, I think, in this paper. Actually, they discussed it also. So the way that they think about it is that you can yeah, so these operator insertions are like some modifications to the action of JT, and then you can also look at what happens to the dilaton. They actually draw the profile of the dilaton and so on. So yeah, so there it's actually, yeah, actually they even the words that they say are actually, this paper is before the stories with the wormholes, and the words they say are very similar to what happened, to what solves the information paradox in the wormhole story. So I think what you're saying makes a lot of sense. And the question is, in this case, it's like this is not only low temperature, then I don't know how to describe it in terms of a dilaton. But yeah, I think what you're saying makes a lot of sense. Yeah, that's exactly what happens there also in the page curve story.
Yeah, somehow it's yeah, I wonder if the lesson is that even in this double scaled theory where the geometry is more nebulous, there is still some kind of information paradox, and it's resolved in the same way. Usually, to formulate the information paradox, one requires a semi-classical description.
Right.
But here you have a geometry which is, it's semi-classical in a certain limit, but then one loses control as
Right.
you go deep into the bulk. But somehow there is still a paradox that you can write down, and it's being resolved in the same way.
Right. Right.
Yeah, it's very interesting.
Yeah. So the question is how to phrase it in terms of the bulk, right?
Yeah.
Yeah.
That probably requires some understanding of this high curvature region. Are there modifications to JT which can suppress the curvature like this, which can send it to very large negative values in the deep bulk?
Yeah. So I guess if we include like yeah, so maybe even if we just include some potential to the dilaton, maybe that would be enough, because it will fix R not to be a constant, but something that depends on the dilaton. Maybe with some function of the dilaton, it will give you, yeah, maybe it will give, yeah, it can give you some profile that is non-trivial. I actually didn't try to do that explicitly, but adding some potential to the dilaton can do the job maybe. And then yeah, and then you can phrase it in a similar way.
So in the maybe I misunderstood something, but so there is a phase transition in which diagram dominates. What I'm not seeing is, let's see, there's no notion of wormhole here, right?
I mean, this is like a two-sided thing, right? It's like It's like a wormhole between this like prepares for you the two slides. Yeah.
Well, what I'm saying is that there's no notion of a. I mean the change of diagram that dominates does not involve. Does it involve also a change of type of geometries that contribute? Like what? Because for me, this is just a disk right now.
Yeah, so right.
But to me, what I'm trying to say is that the usual notion of paradox I know is when the disk basically computes the wrong thing, and that you need to consider multiple copies to probe the fact that there are corrections to the disk. And here, I guess I only see a disk. So it's as if the transition happened for, the type of diagram that dominate, but on the disk.
So yeah, so actually I think maybe it could be made more precise. So yeah, let me maybe share. I just want to draw, maybe, let me think. Okay, let me try maybe to share with the iPad just a second, okay? Just one moment. How do we do that? Maybe I'll disconnect from the Zoom here.
Yeah, one way to maybe think about this transition is, so in the system with the end of the world brains in the West Coast model,
yeah,
you can think about those brains in some sense as like a heavy particle that cuts off the geometry.
Yeah.
And there's a sense in which the operator insertion in your picture, if it's heavy enough, will do something similar.
Yeah.
It kind of brings the two asymptotic boundaries close together. And these different pairings of the operators will deform the geometry in different ways. So it's not exactly like the wormhole transition because in the end of the world brain story, there's actually a wormhole, right? Like there's a phase where they're disconnected and a phase where they're connected. Here the situation is such that in one phase of the entropy calculation, the diagram that dominates is squeezing the disk in one direction, and in the other phase, the squeezing happens in a different pattern. So it's not clear from the figures, but there's something geometric about the different pairings.
Yeah, that's along the lines that indeed I had in mind. So there was this paper also of Vijay Balasubramanian, and so they did some analog of this end of the world brain story, but they used the same state that I wrote here. So for them, what happened is that this operator was the analog of the end of the world brain, and it's sort of this was like a particle that you throw into the bulk, and in different geometric configurations, you had to connect these operators in different channels. So the fact that you connect here, so let me still share. So the fact that you connect here this point to this point, it's like you have a geometry that connects this part with this part, and only then this operator can go from here to here. So the picture that they drew is very similar. It's not very similar. It's exactly this, actually. Yeah. So even though it looks like it's one big disk, the fact that it factorizes to products of two-point function, it's as if this one is connected only to this, and this one is connected only to this, and so on. Does it make sense?
I guess, I mean, I forgot. So where is, sorry, maybe I forgot. So right now you're computing the entropy of the pets, right?
Yes.
That's, so the
so there is the state that you prepare is a density matrix that has an operator insertion, two operator insertions,
Yes.
up and down, and two open legs for the matrix indices. Where are they in this drawing?
So here, so this is this. You see the pointer, right?
Yes.
So this is one end, and this is the other end, and these are the two operator insertions. So if you have only this part, it prepares one density matrix. So here what I calculate is trace rho to the power 4.
Yes.
So I glue the left end here to the right here in, and so on.
I see. Okay. So so something is cut off, right? In this drawing, something is to be thrown. No.
What do you mean?
So you see in the so the dots are the operator insertions. So sorry, no, that's the connection of the
So these are the this means that I look at the 2-point function of this dot. And this 2-point function, I need to recall exactly the drawing in their paper that they had, but the fact that I want to connect this operator to this operator, when I maybe this drawing is actually more confusing than helping, because the fact that I connect this one to this one, it's as if they live in a geometry of their own rather than in the same geometry as these guys. It's like this particle goes into the bulk, but not into the same bulk as these ones.
Well, okay. There's one big bulk, and attached. I mean, it's you have a boundary path integral, and you have for both of them you have a fully connected geometry.
So in this drawing it looks like a fully connected geometry, but at the end it's a product of 2-point functions, right? So I guess let me try to recall how they were drawing these things. So they let's see. Yes, so they had these two.
Actually, let me maybe we can keep talking, but maybe let me stop the recording.
Oh, sure, yeah.